Hello, and welcome to today's session on within-subject ANOVAs. Today, when we're talking about within-subject ANOVAs, we're going to focus on two main themes. One will pertain to the assumptions that underlie this statistical test. The other will pertain to the special kind of post-hoc test that we're going to need to analyze a within-subject ANOVA. Some important words that we'll come to understand with regard to assumptions will be Mauchly's test for sphericity, and then also with regard to post-hoc tests, we're going to learn about a new adjustment called the Bonferroni adjustment. Just to set the stage a little bit for today's conversation, I did want to remind us about our research cycle. As psychologists, we are scientists who are interested in three major kinds of real-world phenomena: behaviors, thoughts, and feelings. Usually, those are too difficult to investigate in a very direct sort of manner, so we have to create a research representation of the real world. And we do that using two different procedures. First, we engage in sampling, and it's important that we get our sampling right so that at the very end of our research cycle we can generalize back to the real world. Also, we engage in operational definitions. When we're talking about operational definitions as part of our abstracting process, we're talking about stating the operations that we will use to measure the behaviors, thoughts, and feelings that we might be interested in out in the real world. When we're specifying that measurement, it's often very helpful to state precisely what kind of measurement scale we might use. Recall that we have four different levels of measurement scale. The most rudimentary of these would be the nominal or categorical scale, and this talks about qualitative differences between variables. If we go up one level in precision, we can talk about a ordinal scale, which gives us rank ordering without actually specifying the interval between the ranks. Beyond that, we have the next most precise scale, which would be the interval scale, which does have equal spaces between the items on that scale, but we do not have a fixed 0 point. We have an arbitrary 0 point. And then finally, we have the ratio scale that has the most precision because it permits ratios, as the name would suggest. So when we're operationalizing, we want to make sure we state which particular kind of measurement scale we're going to be using. That'll have implications, too, for the data analysis. But for the moment, we're just at research representation, and once we have that, after having abstracted using operational definitions and sampling, we can go on to any of our three methodologies that we've described so far this semester. And these would include survey methods, observational methods, and experimental methods to derive some kind of research results. Once we have those, we can engage in any kind of data analysis, but of course our data analysis is going to be constrained by the kinds of measurements that we've made, and specifically the kinds of measurement scales that we've had. Today we're going to be focusing mostly on a within-subject ANOVA, which will be the kind of scale, or will be the kind of data analysis we can do if our measurements had been done on ratio or interval scales. With these data, we're hoping that we can reach some conclusions that will generalize back to the real world, and again, our capacity to do that well will depend largely on how well we operationalize things and how well we sampled. Okay, so we're going to talk now a little bit about the within-subject ANOVA within SPSS, but only just for a moment, because SPSS is a helpful package for us contemporarily, but software packages come and go. The course is really about quantitative reasoning, and so we want to have you develop some intuitions about the quantitative reasoning that underlies a within-subject ANOVA. That said, I do want to introduce us to a fun fact and something that is relevant to SPSS. So here's the fun fact. It can be shown that there is a formal mathematical relationship between ANOVA and linear correlations. You'll remember that we've introduced previously Pearson's linear correlation with the R statistic. And in Excel, for example, we might put in equals Pearson, we highlight over one column, we highlight over another column, and we get some value between -1 and +1 that shows us the linear correlation between those two data sets. Interestingly, there is an important mathematical similarity between the ANOVA, the analysis of variance, and those kinds of linear correlations like we see in the Pearson R. Any ANOVA is considered a special case of a linear model to mathematicians, and we're not going to go into a formal proof about that, but the reason why I'm making that point today is that when you are inside of SPSS and you're about to get your analysis going, for a within-subject ANOVA, which is today's topic, you would begin by clicking on Analyze, and then the very next click is General Linear Model. And that might seem counterintuitive to you if you hadn't known that the ANOVA is actually a special case of a linear model, one that can be described by a best-fitting line, a straight line of the equation y equals mx plus b, whether that's positively sloped or negatively sloped. Okay, so just a little bit of background there. These next two slides contain some details in SPSS that we'll do in the classroom, but again, we want to focus really on the quantitative reasoning today and not on a particular software package here in this video. So what we'll do is we'll get into the heart of today's talk, first starting out with some assumptions, and then also we'll follow up with some post-hoc tests. Okay, so just to set the stage for the assumptions, let's review what we do know about assumptions for parametric tests. Of course, parametric tests are tests that depend on the mean, and some examples include Pearson's R statistic that we've talked about before, the various t-tests, and the between subjects ANOVA, also called the independent samples ANOVA. These are all parametric tests because they rely on a mean. The same thing is true for a within subject ANOVA, and we're going to see here some similarities but also some differences between the within subject ANOVA and the between subject ANOVA with respect to the underlying assumptions. In the case of the between subjects ANOVA, you'll recall that we had something called the equal variance assumption. That also goes by a synonym called the test of homogeneity of variances. This homogeneity means equal or equality between the variances. And the idea here would be that if we had, say, two or more groups, they would have various means shown here. Sometimes the means are higher, sometimes the means are lower. They also have variances that we can gesticulate by doing this with our fingers. We can have equal variances, or we can have very unequal variances. Here's a large variance, here's a much smaller variance, and we would use the Levene test to tell us about equal variances before we went on to test the null hypothesis. Recall that that was a two-step process, that we looked first at the equal variance assumption using the Levene statistic, and then subsequently, if that had been a safe assumption, we would proceed on to test the equality of means, which is the null hypothesis in ANOVAs. Here again, just to refresh your memory, we're not interested directly in the Levene statistic. We're really interested in the sig value associated with the Levene statistic. More specifically, the sig value here is greater than 0.05, so in this case we would wind up retaining the equal variance assumption. Maybe the two variances were both equally large or equally small, but they were sufficiently similar to each other to pass this first step in our two-step process of equal variance first, and then an evaluation of equal means. Okay, so that's what we've done before in the between subject case. We're going to see something a little bit similar, but a little bit different in the within subject ANOVA case, and that's what we have here. What we can see is that the repeated measures ANOVA is based on the sphericity assumption. And as a matter of fact, we're going to make that one of today's mantras. Would you say it with me, please? The repeated measures ANOVA is based on the sphericity assumption. There you go. I knew you could say it. So we don't have an equal variance assumption, but we still have a two-step process. The two-step process now is an evaluation of an assumption, just like it was in the between subject case. There we were evaluating the equal variance assumption. We'll swap that out, and we will swap in the sphericity assumption. We have to evaluate this first, and then after that's evaluated, we can drop down to step 2 and evaluate the null hypothesis, which, as always for ANOVA, will be an evaluation of the equality of means. The null hypothesis for a within subject ANOVA is just like it was for the between subjects ANOVA, and that is that in the population, all means are equal. But before we get that far, we do have to evaluate an assumption. This time it's sphericity rather than equal variance. So let's see if we can learn a little bit about the sphericity assumption and what it means. It's just a little bit more complicated than the equal variance assumption, and in fact there are some complications that are beyond this course. But at least we can begin with some kind of intuition about the sphericity assumption. So here it is. Sphericity assumption might be defined as the correlations among scores in the various conditions are equal or close enough. Okay? So we can have maybe say 3 different conditions in our within subject ANOVA, and we want to understand what the correlations are like across those. Strictly speaking, it's more complicated than that, but that's close enough. Let's see if we can unpack that just a little bit. Let's assume that we have 3 different conditions, A, B, and C, and this is what the sphericity assumption would say about those. The correlations between condition A and condition B would have to be equal to the correlation between condition A and C, and that would have to be equal to the correlation between condition B and C. So all the pairwise comparisons would have equal, or at least similar, correlations. And to the extent that that is true, the sphericity assumption is safe. To the extent, though, that that is not true, we have a violation of the sphericity assumption, and we'll have to take some corrective action. We might, for example, choose not to conduct the ANOVA because we think the assumption is not sufficiently safe, or we might have to make some kind of an adjustment that we'll get to in just a few moments. Okay, so let's just see if we can draw that on the board. I'll break out of this for a moment. And we'll take a look at what we really mean by the sphericity assumption. So to get us started, we'll remind ourselves that we're going to take an example of a within-subject ANOVA, which is also called a repeated measures ANOVA, and we're going to compare, for example, performance on, we'll say, research methods final exam scores before we take the test, before we take the course. So we might, for example, have on the first day of class, time 1, this will be condition A, we give everybody, hypothetically, the final exam on the first day of class. You might imagine they wouldn't do so well on the first day of class. Then, at time 2, we'll call that condition B, we'll give them the final exam during the final exam period after they've taken the full semester course. Presumably, we'd be better here than we are over here. Just for fun, we could even posit a third condition, and that is when you come back for your 50-year reunion here at Denison, we could measure you, hypothetically, on the same research methods exam, and here at time 3 we'd have another set of scores for the same students that we've had all along. So we have repeated measures on the same exam across 3 different time points, A, B, and C, time 1, 2, and 3 in this particular case. Okay? So the idea about the sphericity assumption would be something like this. If we were to say equals Pearson and highlight over this set of scores and this set of scores, we'd get a correlation between these 2 conditions, and that correlation would be some R value. I'll leave it at a question mark for right now. Then what we could do is we could compare you later in life, when you're coming back for your 50th reunion, to how good you were at the end of this course. We could make that comparison as well. Again, with a equals Pearson, we highlight this column, comma, highlight that column. We come up with a new R value. And we could begin to take a look at the sphericity assumption by asking the question, is that R value and that R value, are they relatively similar to each other? Are they approximately equal? There's one more comparison we could make, and I'll do it this way. We can compare condition A to condition C by way of this Pearson correlation, and we can get one more R value, and we can ask how similar are these R values to each other. The actual sphericity assumption is more complicated than this, but this might give you an intuition for what it's about. It's not as directly about the equality of variances. There is this other concern that we have an equality of covariances. And to the extent that these are similar, then the sphericity assumption is going to be safe. To the extent that they're very different, the sphericity assumption is going to be not safe, and we have to take some kind of corrective action. Okay? One other point, and this will be a subtle point about the sphericity assumption, but I think you might find this interesting. Let's say that we have an ANOVA, very similar to the one that I have here, but it's even a simpler ANOVA. It's within subjects, it's repeated measures, but it contains only 2 conditions rather than 3 conditions. In this case, we can get rid of, for example, time 3. That goes away. And because that goes away, we now have only one correlation that we could possibly have, and that's between these 2. And whatever that value might be, there's nothing to compare it to. There's no other correlation that can be made. We only have the 2 conditions. And because this is the one and only kind of correlation that can be made, we can say that the sphericity assumption can never be violated in this case. It is always safe to assume sphericity if you have only 2 conditions. The sphericity assumption only gets called into question once we introduce a third condition or more than 3 conditions. In fact, whenever it's more than 2 conditions, we would have to check the sphericity assumption. SPSS and other software packages won't even compute a sphericity assumption for you. They will not give you a sphericity value through this test called the Mauchly test if you have just 2 conditions. If you have 2, you're automatically safe. It's when you introduce the third one that we have the problem, because we would automatically have just one R value if we have 2 conditions, and that doesn't have a comparison, or no comparison can be made if we don't have a third condition. So that might be a good extra credit question. Why is it the case that we don't need to compute Mauchly's test of sphericity if we have only 2 conditions? You might think that one through, and maybe that'll be an extra credit question in class. Okay, let's go back to our regularly scheduled program. And And we'll talk a little bit about that specific test for sphericity. Again, as I've mentioned a few times now, this is called the Mauchly's test of sphericity, and it's used to indicate whether the sphericity assumption is safe or not, whether we should retain or reject that assumption. So let's take a look at where this might be in the SPSS output. This is landing in a place roughly akin to where the Levine test would have landed in SPSS output, and that is to say that we typically look at this first before we evaluate the null hypothesis in our two-step process. We evaluate the assumption first, and then secondarily we evaluate the null hypothesis. So here's the sphericity test called Mauchly's, and we're always interested in the sig value. And in this particular case, because the sig value is less than 0.05, we reject something. In this case, we reject the sphericity assumption, and we have to take some alternative step. We can't just take the ANOVA for granted. We have to make some kind of adjustment to the ANOVA value that we see, because the assumption on which the ANOVA is resting is not safe in this case. We have to reject the sphericity assumption. Okay. So if this value had been greater than 0.05, we could assume sphericity, but because it's not, we have to make some kind of adjustment. And now it gets just a little bit complicated. We'll see if we can walk you through this. Assume that you do have to reject the sphericity assumption. What do you do? Well, fortunately, SPSS gives us a few different alternatives. What we're going to be doing in our class is we're going to wind up taking advantage of the second line down here, the Greenhouse-Geiser line. If we, in fact, we can assume if we can assume sphericity, we'll stay on the top line here and we'll go with that sig value. But if we can't, we'll drop down one line and we'll go with the Greenhouse-Geiser. Okay? So just to remind you of where that would be, here's the second line down. If we reject the sphericity assumption, we'll stay with the Greenhouse-Geiser. To be fair, different statisticians would come to different kinds of conclusions. There are different ways of making the adjustment to the sphericity violation. And you could use an adjustment called Hoyenfeld. You could use an adjustment called lower bound. We'll see how these differ from each other in just a moment or two. But we're going to, as a matter of procedure in our class, stay with the Greenhouse-Geiser as our adjusted value, our adjusted sig value, if in fact we have a sphericity violation. On the other hand, if we have no sphericity violation, we can assume sphericity and we'll stay on the top line as shown here. Okay. So how is it that these adjustments are made? When we say that we have a Greenhouse-Geiser adjustment, what exactly is going on? Here's the idea. We take advantage of something called epsilon values when we have a sphericity violation. And the epsilon values are shown here for different kinds of adjustments. This is just like the earlier case of having different kinds of post hoc adjustments. We have different kinds of adjustments for sphericity violations. We're going to be using the Greenhouse-Geiser, and we could have used any of the other two. I think for explanatory purposes, it might be helpful to look at the lower bound just for a moment. When sphericity is not assumed, the degrees of freedom are adjusted according to the epsilon values. These values almost become coefficients, kind of like the coefficients that you learned about in 7th or 8th grade, or in the simple y equals mx plus b equation. M is our coefficient for the slope. Here we have coefficients by which we will multiply the degrees of freedom. Let's take a very simple example of the lower bound 0.5 adjustment that we have here. 0.5 becomes our coefficient. Let's see if we can apply that to our SPSS output. Here's the output for the within subject ANOVA, and here's the line for assuming sphericity. Okay? In our class, we're typically going to assume sphericity unless we have a violation, then we'll drop down and do the Greenhouse-Geiser. Just to show you how the Greenhouse-Geiser or any of these other adjustments work, we'll recall that 0.5 value, the epsilon value from the lower bound adjustment, and we'll now multiply the degrees of freedom for our factor 1, that's our between conditions factor. We'll multiply that 2 by the scaling factor or epsilon value of 0.5. 2 times 0.5 gets us to 1. We can play the same game down here for the error term. This represents the within condition variability, really the size of our error bars. Initially we had 34 degrees of freedom. If we have a sphericity violation, we typically adjust the degrees of freedom according to some epsilon value. The epsilon value for the lower bound was 0.5. So we'll multiply 34 times 0.5, which is essentially cutting 34 in half, and we now have 17 degrees of freedom. So notice that if we have a lower bound adjustment, we've made a relatively conservative adjustment. We've basically cut the degrees of freedom in half. When that happens, that usually makes it harder to beat the number to beat. And I'll draw that on the board now also. So we've seen before that we can have the F distribution. And the F distribution is positively skewed. It looks something like this. It starts at 0. It goes off to positive infinity with this right tail, or what we call a positive skew. And there's some cutoff region right over here that we call our critical region. And you might remember that it starts at 0. It goes off to positive infinity. Here's the critical value. That's the number that we have to beat if we want to statistical significance. It peaks at 1, which would suggest that we have as much variance between our conditions as we do within our conditions. And of course, this is simple probability, with relatively high probability occurring at 1, and lower probabilities as the F statistic is getting larger. What goes on when we have a sphericity violation is we, as you've seen before, we make an adjustment to where this boundary is. We basically lower the degrees of freedom. By doing that, we're effectively moving this line out further and further, and we can move it out space amounts. In our case, we go with the greenhouse Geiser amount. In other classrooms, they might have come to a different conclusion. Maybe they would use the lower bound or some other kind of adjustment. Okay, so that gives us an idea about what's going on when we have a violation of this important assumption for the within subject case, which is the sphericity assumption. All right, let's see if we can have you pause the video. We'll come back in a moment and talk about our next major. Okay, welcome back. Okay, welcome back. So as we mentioned at the top of this video, we would talk about two primary components. One would be the assumptions that underlie the within subject ANOVA, and we talked about sphericity. Now we're going to move on to the post-hoc tests, and we'll see how these are a little bit different in the within subject case than in the between subject case. To get us started, let's do a little refresher. Here's a review question. What were the two reasons for using post-hoc tests? We'll let you stop the video and see if you can recall those two. Okay, welcome back. As you might remember, the two general ideas were that the omnibus ANOVA doesn't tell us where the individual differences might actually be within the pairwise comparisons. It might be that we have only one pair of means that are actually different from each other. And we'd run a bunch of t-tests to reveal that, but the omnibus would not. So we need the post-hoc tests to pinpoint where the differences are. And that's the first component. The second component is that the post-hoc tests also control for this cumulative type 1 error. And this will be true both in the within subject case and in the between subject case. Unfortunately, it turns out that some software packages, including SPSS, don't perform post-hoc tests for within subject ANOVAs. So that being the case, we have to move on and see if we can somehow manually compute the post-hoc corrections that we would otherwise get automatically out of SPSS. We can isolate the particular means that might be different from each other by using t-tests, just as we had done in the case for the between subject design. We'll also have to now control, though, for cumulative type 1 error in a manual way. And so we'll see if we can move on to understand what that is. And that manual procedure is called the Bonferroni procedure. And to get us started on the Bonferroni procedure, we're going to make a mantra out of the first portion of this sentence. I'll read it to us once, and then we'll say it together. The mantra will be, the Bonferroni post-hoc adjustment controls for cumulative type 1 error. Can you say that with me? The Bonferroni post-hoc adjustment controls for cumulative type 1 error. And we're going to use the Bonferroni as our manual adjustment for the within subject case. Okay, so to read that whole thing one more time and continue in our sentence here, we'll say that the Bonferroni post-hoc adjustment controls for cumulative type 1 error among the repeated measures test by multiplying each observed alpha level, which you remember is called our sig value, by the number of t-tests that we've run. And we'll take an example that we hope will motivate this and make this really clear to you. Here's an example. If we run 2 t-tests post-hoc, that is after the fact, we would multiply each observed alpha level, which is the sig value, by 2, because we ran 2 t-tests, and compare that to the 0.05 alpha level as we've always done. All right, so the idea would be that we conduct the t-test, we look at the sig value, and then we have to scale that up by some multiplicative factor. Now, the new Bonferroni adjusted sig value for a particular t-test in SPSS would have to be lower than 0.05 for us to claim statistical significance. Okay, so we'll take an example here that I think will make this really quite clear. Let's assume that we've run many comparisons in our omnibus test, and we get some good news. The omnibus F tells us that one of these things is not like the others. We actually get a significant sig value from the omnibus within subject test, and we've already satisfied, for example, the sphericity assumption. So then we might proceed and run something like, in this particular case, 5 different t-tests. Maybe we had 5 tests that were of interest to us. Let's pretend for the moment that one of those t-tests produced a sig value inside of SPSS that was equal to 0.015. The question here is, would we retain or reject the null hypothesis in this case? Okay, so we'll let you think this through. You can stop the video and see what kind of answer you come to. Okay, so welcome back. This would be the procedure for the Bonferroni correction. We would take the 5 tests and we would say, okay, there are 5 of them, so we're going to scale up our observed alpha level, our sig value, by a factor of 5. If you multiply 5 by the observed value of 0.015, you'll come up with a product that is 0.075. And 0.075 is greater than the criterion alpha level of 0.05. So in this particular case, we'd wind up retaining the null hypothesis, not rejecting it. And this is kind of interesting because here we can see that we do have a sig value that is at least nominally lower than 0.05, but after our Bonferroni correction, it's actually greater than 0.05. So in this case, we'd wind up retaining. Let's go on to another example where everything remains the same on this slide, except we change 5 to 4. And we can see here that now we've run 4 tests, and the question again becomes, should we retain or reject if we have a 0.015 sig value in our SPSS output? We'll let you stop the video and think that through. Okay, well, welcome back. And the idea here again is that we're going to retain. And the reason is, if we take the 4 tests that we've run and we scale this observed alpha level or sig value up by a factor of 4, because we've run 4 tests, we would have 4 times 0.015. That works out to be 0.016 and 0.06. And 0.06 is greater than 0.05. So we just missed in this case. 4 times 0.015 gets us to 0.06, still greater than the criterion alpha level. We still can't reject the null hypothesis. We have to retain it. Here we'll go on one more time, and let's assume that we run the test now with 3, where we run 3 t-tests, and we're making the Bonferroni correction with 3 t-tests. Here, we'd take the 3, we'd multiply it by 0.015, and we'd be at 0.045, which is ever so slightly less than 0.05, so now finally we can reject. What's very interesting about all this is in all 3 of these cases we've had a 0.015 observed alpha level, at least nominally, but whether we retained or rejected depended on how frequently we were testing and what kind of correction we had to make through Bonferroni. If it was 5-fold, we didn't have a sig value that could survive the correction. If it were 4-fold, our sig value did not survive the correction. But in this particular case, the 3-fold scaling up of this observed alpha level still was underneath the criterion 0.05, so we were able to reject the null hypothesis. Let's take a look at another case. Here we have 2 t-tests, so we're going to scale up our observed alpha level by 2, and the observed alpha level, at least nominally, was 0.04. That was our sig value. So here, in this case also, we'd wind up retaining the null hypothesis because 2 times 0.04 gets us to 0.08. 0.08 is greater than 0.05, so we're going to retain the null hypothesis. Okay, let's do one last one. Let's assume that we have 2 t-tests, and we have a 0.015 alpha level. Here we scale the 2 t-tests by the 0.015, and we wind up with 0.03. 0.03 is below the criterion alpha level, as always, of 0.05. So here we're going to wind up rejecting the null hypothesis. So it's very interesting that our ability to retain or reject the null hypothesis is going to be contingent not only on the observed alpha level, but on how many t-tests we've actually had to run. And so you might choose to become very judicious in picking the t-tests that you run, because as you run more and more t-tests, you'll have to make larger and larger adjustments according to the Bonferroni correction. Okay, so that's as far as we want to go today. We've had lots of ideas in today's conversation. We mentioned that the within-subject ANOVA has some similarities and differences with the between-subject ANOVA. They both have assumptions. The assumptions are tested along this two-step process. The first one is the test of the assumption itself. The second one is the test of the null hypothesis. In the case of the within-subject ANOVA, we learned today that we have to test the sphericity assumption. And the critical name there was the Mauchly test. In fact, that might be a good pop quiz question or a good extra credit question. It might be something like, what does Mauchly's test do for us? Relatedly, later in the video, we learned that Bonferroni's test, or Bonferroni's adjustment, also does something for us. Specifically, the Bonferroni adjustment gives us a correction to our cumulative type 1 error problem. And it does so in the within-subject case through this simple scaling mechanism. So another good pop quiz or extra credit question might be, what does the Bonferroni test do for us? I hope that you'll make your notes in PowerPoint, right next to your PowerPoint printout, and indicate what's been very clear about this and also what might be made more clear in class. See you in class.